We already talked about a couple of algorithms and index structures in the previous videos, and also a couple of other things. So for example, we talked about data layouts, for example. So data layouts was one thing we talked about in the context of data management. But the question for all of these techniques is, which is a better one? And how do you determine which of those techniques is a better one? That is what this video is about. So what we considered in most of the discussions were very simple things. So one was the amount of data read and written, or here and there the random I/O versus sequential. But what we typically ignored are many other things. So we concentrated on these two, but what we ignored was stuff like the database buffer scheduling strategy, the concrete scheduling strategy, and what is the impact of that on the overall performance. Then all the different cache misses. When do those cache misses occur exactly, and what exactly is the performance impact of those cache misses? And of course, it depends highly on the concrete architecture that we're using, the size of those caches and the latency of those caches and so forth. Then the different bandwidth among CPU, caches and memory. The closer you get to the CPU, as you remember from the storage hierarchy video, the closer you get to the CPU, the higher the bandwidth of the caches. We didn't really consider that when determining performance. Well, then the CPU costs. What does it mean for an algorithm? Is it one core or multiple cores in the CPU we're using? What is the effect of that? Then multi-threading. There are a zillion effects in multi-threading, especially with respect to the caches. Example, if you have threads that operate on the same cache lines, so something like that, thread 1, thread 2, and they both want to work on the same cache line, let's call it CL1. However, they're scheduled to different cores, and then they might steal each other's cache lines, and that has a huge impact on performance. And there are many other effects in that context that you really want to consider for that. Then of course hyper-threading. So even if your operating system says you have 8 cores, maybe it's just, actually this is 4 plus 4, so maybe it's 4 physical cores. Yeah, so it's physical cores. And 4 hyperthreads. And what a hyperthread can do is different from what a real core can do, and that has an impact on performance, of course. Maybe you should consider that when trying to understand the performance of a specific algorithm or index structure. Then, of course, all these scheduling effects that may happen. So this is similar to the problem I depicted above. So where exactly are those threads scheduled by the operating system? Do you maybe want to take over the scheduling? Do you want to force a thread to a specific core? Maybe that's a good decision. That decision, which data sits in which L1 cache, has a huge impact on performance in a multi-core environment. Yeah, then on the disk level, if you read data from disk, of course, what exactly is happening on the storage level? So how many disks do you have? So what is the performance of those disks? What is the RAID level you're using? And so forth and so forth. Yeah, then all the data distributions and data skew. Is it a uniform distribution? Is it a skewed distribution in whatever sense? What is the impact of that to the performance of the algorithm? Could it be that for a uniform distribution, typically you have something like that. You have a uniform distribution, and then you get one number. If you just measure it end to end, maybe you get 42 seconds. If you have a skewed distribution, then maybe you measure whatever, 120 seconds. So that's a huge difference just by saying that your algorithm runs 42 seconds. This is maybe not the correct way of saying that, because then you assume that the distribution is uniform, the data distribution is uniform. So those distributions have a huge impact on the overall performance. And the same holds for the workload. Workload distribution here means if you have a domain, say, let's make it really simple. Let's say you have a domain from 0 to 100, integers in that range. Uniform workload would mean you have a where clause, a equals x, and this x is uniformly distributed in this range here from 0 to 100. That would be uniform distribution with respect to the search predicate, with respect to the where condition. However, if your queries are only interested in a specific range, let's say 0 to 10, yeah? So whatever where condition you hit, it's in this range, even though the total domain is within 0 to 100, then you have a skew. So skew meaning it's concentrated on a specific sub-area here in that range. So that, of course, has also an effect on the overall performance of an algorithm. Yeah, then stuff like SIMD, that's other multi-core stuff. So can you use that? Does it have an impact on your algorithm? Yes or no? So we will look at that in separate videos when talking about main memory databases, but it has an effect. And there are many, many other things we typically ignore when trying to analytically understand the performance of algorithms or index structures. So how do we approach that? So how do we measure performance? Well, the good news is there are actually only 3 ways to measure the performance of a computer program. And those are the 3 approaches. So the first is analytical modeling. So analytical modeling means you have some sort of analytical model and you try to reason about that. So typically what you already know about is this O notation. And then all these complexity classes that people come up with to understand the general properties of the runtime of an algorithm. So we will look at that in a moment. So at the high level, for the moment, analytical modeling means you come up with some sort of mathematical model. There's some sort of mathematical model. So the second approach is a simulation. Simulation is about faking realities. So rather than executing the algorithm in an environment with real data, with real queries, with a real machine, you somehow simulate the effects. And that's another important approach to measure performance. And the third approach is, of course, doing an experiment. But actually, in between those, there are different hybrid approaches. So it's a simulation where parts of it feel like an experiment, or it's an experiment where parts of it feel like a simulation, however you put it. And the same holds in between 1 and 2, of course. But let's focus at the 3 high-level points for the moment. Just before we get into more detail for these 3 ways to measure performance, it's important to understand whenever you measure the performance, it's a good idea not to only use one of them. So if you just use analytical modeling and then there's a bug, assume that there's a bug, okay, then it might be very unfortunate if you draw any conclusions based on that bug. Of course, if you also use a second approach like simulation and an experiment at the same time, then it becomes very unlikely that you see the same bug there. So there's a certain likelihood that one of the ways to measure has a bug, the other has not. And as you then obtain contradicting results, you will detect the bug early. So whatever you do, it's a good idea to combine those approaches. Take 1 and 2, for example. Take whatever, 2 and 3, for example. And then the simulation gives you one thing, maybe that's a simulation, gives you this curve. Whatever is here on those axes doesn't matter. So maybe that's a simulation, and the experiment maybe gives you this curve. Yeah. So there's some correspondence, and how to determine how they correspond is another story. But if the experiment gave you something like that and the simulation something like this, well, then you have to look at that. Then you have to investigate and find out why the heck is there a difference. Is there something wrong with my simulation? Is there something wrong with my experiment? And if you make sure that the effects that are predicted by the simulation are similar to the effects you actually measure in the experiment, then you gain a lot of confidence that what you obtain in terms of performance numbers makes sense. So it's important to combine 2 of them, or you can also combine 3 if you want, but it's obviously a little risky just to solely look at one of those. In the end of this video, I will also contrast the 3 methods again. But before doing that, let's look at that in some more detail. So, analytical modeling, usually what you learned about already is this asymptotic complexity and the O notation. So what that means is you have some sort of model, which means you count each primitive operation as one. So typically arithmetic operations, node hops in the tree, memory accesses, page accesses, and so forth. You have a model in your head. So for a binary search tree, for example, if this is your binary search tree, let's draw a tree. So here's our tree. Okay, it's a small tree, whatever. You say, so whenever you are on a node, whenever you do a hop, then you count it as one. So here, that counts one. And then you make a decision to go down left or right. Let's go this way. So there's another node. Yeah, that counts another one. And then you're here, maybe that counts another one. Depends on whether you want to count that or not. Let's assume you count it. And then this gives you 3. So 3 hops in the tree. And then, of course, in all these discussions on data structures, then you can make discussions like, okay, what is the worst case complexity, what is the average case complexity, blah, 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 blah. And then based on that, and then you design index structures that have specific properties, that have good runtime complexities with respect to O notation. So important here is you only determine the asymptotic complexity of the index. So which means if you have a function that determines the number of operations you do, let's say that's a function n, and it has something like n squared plus whatever n log n. So what O notation does is it kicks out all the terms that don't have so much influence once you increase n. So basically a function like that will lead to an O complexity of n squared. As for large n, that term doesn't matter anymore. So if you're unsure about that, take a look at videos on complexity, asymptotic complexity, look at the undergrad courses on the definitions of the O notation. I'm not going to go into detail here. For us here, it's important to understand that this is a very high-level tool. O notation is a very high-level tool to argue about the complexity of a specific algorithm or index. And in many, many situations in databases, it is just not enough. It's not powerful enough to really understand the performance of a specific algorithm. So that's what I said. You have the worst, best, and or average case and so forth. Yeah, there's another tree example. In a balanced binary search tree, you have O log n average and worst case. Time. And that's the crucial thing to understand. What does time mean? Because the time we are talking about here is not the time in reality. This is a time with respect to the model you have in mind. So if you go back, so what is the model? I said the model here could be something like the number of tree hops, and that is what you count. And that is your notion of time. However, that notion of time, so model time, let's call it. And then there's reality time. So what is, for example, the end-to-end time? Unfortunately, there may be a gap among the two. So even though the model says, this is optimal, in reality, this is not the best that you can do. And this is because the model might not predict the major components, the important components to use in such an index structure. Especially for index structures, we will look at certain examples for that. So you might have learned in undergrad courses that this is a good idea and that this balanced binary search tree is a good idea to use, but there are way better structures that are better with respect to the end-to-end time, even though they are in the same complexity class as an AVL tree. And that's another effect of the classes. Even though you have two structures that have the same complexity, they're in the same complexity class with respect to the search time. In the model, with respect to the model time, in reality, the search times may differ a lot. And that is a problem with the O notation because it's sometimes too imprecise, it's too high level. So I'm not saying that this is a bad tool, it's a very powerful tool, it's a good tool, but just O notation alone is not enough for data managing purposes. And there's one problem and this is the problem I just explained. Memory hierarchy is totally ignored among many other effects. So in the following, I'd like to explain that using a concrete scenario. And the scenario is, let's assume a pyramid and you want to walk up the pyramid. And the question is, what does it cost? How long does it take you to get up to the top of the pyramid? And that's what we want to understand with our three techniques. We are in analytical modeling for the moment, so we first have to come up with a model of this reality. Well, here's our model of the pyramid, and then what asymptotic complexity typically does is, in a simple way of using it, would be to count the number of steps. Like the steps in a tree, we would count the steps it takes us to get up to the top of the pyramid. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 steps, that's fine. And that would be the cost. So actually here wouldn't be a difference of that function n, which gives you the costs as a number of steps. So basically f on n is n. And this, of course, has the complexity class is linear with respect to average, worst, and best case. And there wouldn't be a difference among the function and this O notation. So we don't leave stuff away. But anyhow, so the model is really, really simple. Well, and one problem with that is that it really oversimplifies reality, this model. So what actually happens here is, as long as you're walking on the sand, everything is fine. It's relatively easy. So it gets easy until here. But it is painful to actually climb the pyramid. So up to this point here, you have different costs. Yeah, that's cheaper. That's cheap. But once you're here, it's really expensive. And that should be reflected. So let's give it a try. How would we do that? Well, what we do is, in databases, we quickly come up with cost models. So we integrate more factors. We try to understand, okay, what is the number of random IOs? And then we try to count that. So for example, we could say, rather than counting 1 for each step, we say, so whenever it's a random read or write of a page on a disk-based system, we count this as 100. In contrast, if it's just a sequential read or write of a page, we count this as 1. And then we sum it up and then we obtain a number. Well, this might still have problems, so it still ignores CPU time and cache misses, but that's another story. So let's first look at our example with a pyramid. So in a cost model, you also try to have a very abstract model of the pyramid, but then what you end up having is something like that. So that's what I just said. It's really cheap until you get to the pyramid, but then once you start climbing, it's expensive. Every step here hurts, and then you just add those numbers up. 1, 2, 3, 4, 5, 6, 7, 8, 903. That would be the cost predicted by that cost model. And of course, then you can extend those cost models to factor in other things. For example, you could say, well, I also count the number of cache misses. Whether that makes sense or not depends, because if the total costs are dominated by the random I/O from disk, maybe you won't feel a difference by doing that, but that really depends on the algorithm. So let's assume we count that as well. And then the examples for that from data structures, for example, there's a structure that's called the CSS tree that has this property that it has log m n cache misses. So that's very nice. The number of cache misses is not with respect to a base 2, it's with respect to the base m. And m is the number of outgoing arrows of a index node. And that's a huge difference and has a huge impact on performance. So many cache efficient trees have similar performance characteristics. So B trees in memory have a similar effect, B trees in main memory. We will look at that later on. Okay, so, but the problem with those cost models is still, it of course oversimplifies. So it's a model. Huh? So as with any model, you leave stuff away. That's the art of abstracting. So some things are considered and other things are left away. So it might be that for a specific algorithm you're trying to understand, the CPU time has a much higher effect than all those cache misses. And then you have a problem, because then the cost model is not going to predict the performance very well. However, so if you look at this model with a pyramid, what this cost model would mean is, okay, we don't only count 100, we also have costs for cache misses here, and then maybe we end up with something like that. So we have very different effects here. It's not only 100 for each step, you have stuff like that. And maybe here, because some value was cached, it's not a random I/O, maybe you only pay 42, whatever. So you get a more precise cost model that's closer to reality, hopefully. Okay, so, but when getting back to the pyramid, very often you feel like there are so many factors influencing the performance. So far we consider that this is really cheap, but what we ignored is that actually on this day the worker has a bad day, the guy who's running up the pyramid has a bad day, and he is really slow. We also totally ignored that the sun has a huge effect on the performance of the guy walking up the pyramid. So maybe he forgot to bring enough water to drink and then he's slowing down because he gets thirsty, stuff like that. So we didn't model that in the analytical model so far. And then there might also be strong winds, and the strong winds may make it very difficult to climb up the pyramid. So those are other effects we totally ignored in the analytical model so far. Of course, we could also try to integrate that into our cost models, but usually that's very difficult to do. So at that point in time, you typically decide to use another method for performance measurement, and that is a simulation. So in a simulation, you run parts of the actual algorithm or system. So you simulate other parts maybe, yes? Some of the parts are actually executed, which usually in computer science means you run parts of the algorithm like in a lab environment. So the algorithm maybe is not embedded into an overall system, but at the interfaces you simulate things. Well, what the problem with that is, it might still oversimplify reality. So maybe it is better, maybe it gives you a better understanding than the analytical model, but it might still oversimplifying stuff. You might miss some important effects from reality. So it has a similar problem as the analytical models. Once you simulate something, you have to make sure that the major effects you're interested in, the major measures you want to understand, are simulated. If you don't do that, you might be oversimplifying reality. And then what you learn from the simulation is limited, because in the end you want to understand the real thing, you want to understand reality. And if the simulation is not able to predict what reality is about, it's a bad simulation. So in terms of our pyramid, what this means is we have to kick out the real pyramid and somehow have to build a model of the pyramid. And then we have to simulate the same effects we see in reality. So this is easy, yeah? So till we get to the pyramid, it's easy. This work has a bad day thing, I don't know how to simulate. Let's ignore it for the moment, but here this is painful. If you ever stepped on a Lego brick, well, this is really painful. But then there are other things. So this sweat thing and the sun and the dehydration, how do we do that? Well, this is kind of a problem because there's a different temperature depending on the time of the day. So this is an outside influence. This is an outside influence. And we want to control that better. So we better kick out the sun and replace it by something that can be controlled. So for example, a lamp. So maybe it's not as hot as the sun, but we can just switch it on and off at any time of the day. And so we can control it. That's what we do here. We control this. Of course, we also lose something because it's not as hot as the sun. The light is not so bright as the sun and so forth, but maybe it's enough. Well, and we have a similar problem with control here. So how do we do that with a strong wind? So if you just put the pyramid outside, sometimes there is wind, sometimes there's no wind. So we don't have a controlled environment. So what can we do about that? Well, we could also make sure that we put the pyramid in a closed building and then we just get some fans that simulates the wind. So that would be our simulation. So with this simulation, we obtain some results that hopefully allow us to learn something about reality. But then again, this might still be oversimplifying. So if you look back at reality, you might find out, well, what we did so far is kind of oversimplifying. So things you might detect is, well, this is nice with the wind, but you will also see that the wind speed differs a lot depending on the height. So whether you're here, or here, or whether you are here still on the sand, maybe it's like that there is no wind at all here, but then there's a lot of wind and the wind speed is increasing the more you go up, and that has an impact on the overall time it takes you to go up the pyramid. So we haven't considered that so far. What we also haven't considered is the sand dune. Here it gets a little difficult to climb over that, and that increases the time it takes. Well, and actually you learn that the size of the shoes has an impact, because the smaller the shoes, the more you sink in, the bigger the shoes, the faster you can get. It's similar to snow. It's a small effect, but it has some impact on the performance. Other things might be that the angle slightly varies depending on where you are on the pyramid. So that again has an impact on the performance. So bottom line, what I'm trying to say is many other effects you see in reality and you might totally ignore when looking at the simulation. And that is a problem because this might have an impact on the overall performance. And of course, when designing a simulation, the art of designing simulations is to identify the effects, identify the stuff that has actually the highest impact. The art of simulating, the art of modeling is to leave the right stuff away and not leave the important things away. What this means is that in reality, eventually it makes sense to look at an experiment. So you implement it, you run it, and you measure it. So then you have kind of the real thing in a real environment, hopefully. Still, this has problems. So it is lacking abstraction. It might be that actually the experiment is overfitting to a specific scenario. Overfitting means, so what you learn is with respect to a specific hardware, with respect to a specific implementation, with respect to a programming language, stuff like that. So it's overfitting. So many things have been fixed. On the other hand, you learn a lot about the real thing. Yeah, it's lacking bounds, so all these nice bounds we get from complexity theory, O notation, lower and upper bounds, blah, 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 blah. We don't have it here. So it's lacking theory, and sometimes it's also lacking insight. This could be put in brackets. Actually, sometimes you gain a lot of insight by actually implementing it. Very often you implement it and then you see, oh, I totally ignored this feature so far. I totally ignored that there are cache misses. I totally ignored feature XYZ of the hardware. So often you have a lot of insight, but one problem you typically have with the experiments is this end-to-end. So you run it and get end-to-end times, and then you say, whatever, your algorithm takes 42 seconds. But that doesn't explain yet what the algorithm does internally. So just having an end-to-end time is typically not so great. You want to see the components. For example, if you have 3 parts in the algorithms, you want to see stuff like, okay, the first part takes that long, the second takes that long, and the third takes that long. And overall, this is 42 seconds, but the first is 5 seconds. Then you get another 30 seconds, and then you get another 7 seconds. So still when running experiments, it should be the goal to also explain the different effects, the different components that lead to the overall sum of 42 seconds in this example. So overall, to sum up, we have those 3 methods to understand performance in computer systems. So that was the first, that is the second, and that is the third. And there are different trade-offs. So it would be totally wrong to say that one method is better than the other. It would be wrong to say that analytical modeling is the best method. It would be wrong to say that running the experiment is the best method. Sorry, that's not correct. Because there are different trade-offs in all these methods. So when you look at effort and cost, one trade-off you see is typically it's way easier to come up with the analytical model in terms of effort and costs. Setting up a simulation is often much more work, So not always. It can also be that the analytical modeling is so much more complex. However, in the 90% or 95% case, you have a relationship like that. So simulation is kind of okay. It's like in the middle here, and then the experiment is typically quite substantial to run. Of course, it depends. If it's just a small index structure you're evaluating, it might be cheaper. If you're evaluating an entire system, well, that might be some work. But on a high level, this is the relationship you often see. And then there's the second thing that is very different in the different methods, and that is the relationship to reality. So how well do these things actually correspond to what you see in reality? Well, in the analytical model, reality is typically very far away. Well, you can say a few things about reality, but all the details that might have an impact are like abstracted away. Often, not always, but in the general case. Simulation is closer to reality. Experiments are really down to earth. Maybe too much down to earth, because the level of abstraction might be a problem. Yeah, and then the third aspect, the third feature of all of these three methods is generalizability. So here you have a relationship. Well, it's not like that. It's not like that, of course. It's exactly the other way around. It's like this. That is what you see. So in analytical modeling, you have very general results that are important to understand. But in order to build a practical system, they are just not enough. Often this is not enough, especially in data management. At least a simulation is required, but very often you can't live without an experiment. So that's very important to understand. So you see, depending on what you want to have and what you're interested in, you might pick a different method. And as I explained in the beginning already, it's always good style to not only take a single method, but if you really want to understand the performance of a computer system, of an algorithm, of an index, you rather take at least two out of those to understand a specific index or system. If you liked this video, don't forget to hit the like button. Thank you. So if you want to see more database videos, be it in English or in German, take a look at my website datenbankenlernen.de. It has a couple of English and German videos. You can also subscribe to my YouTube channel, Jens did, or you look at our website, infosys.uni-saarland.de. See you then!